Hello everybody, it's Brian Russell. It's been a while since I did one of these talks, but I thought I would share with you a new talk that I gave last week at the Exploration Update. This is May of 2018 in Calgary. And the title of the talk, as you can see on the screen, is New Approaches to Calibrating Time-Lapse Images in Pro4D. So just to give you some perspective, Pro4D is a program that was developed by Hampson Russell for the modeling, calibration, and inversion of time-lapse data. And we have a number of major clients around the world for this program. One of the key steps in the calibration is finding the optimal dynamic time shifts, which will calibrate the monitor surveys with the base survey. In the first version of our software, this was done using a standard cross-correlation procedure, and that's actually still the main option that people use. But recently, we've developed several new options for computing the time shifts. This includes the Taylor series expansion method, dynamic time warping, and Gaussian correlation vector warping, which also could be thought of as vector warp. Well, it is vector warping, but it computes 3 components rather than just one component. So this talk will summarize these methods and show their implementation in Pro4D. But I'm going to start by actually reviewing the older method, the correlation method. So let's start by talking about the data set we're going to be using. It's basically the GLISP pilot, which is a fairly old survey, but it was one of the first surveys, time-lapse surveys done in Alberta. GLISP stands for Reservoir Lake In Situ Steam Pilot. Was done jointly by Amoco and Aostra, which was the Alberta Oil Sands group. And it's about approximately 40 kilometers south of Fort McMurray in Alberta. The base survey was acquired in April of 1985, the first monitor in January of 1987, the second monitor in 1988, and the third monitor in 1989. So this shows the base map for the survey, and the reason it was such a good high-quality survey is they used a permanent source and receiver array. It was all actually buried in the ground, so it made for very reproducible and excellent data. The seismic coverage was approximately 200 meter by 200 meter square. That made a bin size of 4 by 4 meters, 4 meters square. And the frequency bandwidth was very wide, from 20 hertz to 240 hertz. And also 10 wells were drilled in the pilot area. So what I'm going to do is look at the line I've shown in red here, in line 21, which intersects wells H07, H3, and H6. H07 was an observation well, H3 was a production well, and H6 was an injection well. So as I said, their base survey was recorded in 1985, and during the first time period, 3 wells, H3, H4, and H5, were selected for steam injection, and that continued for 15 days, for each well for 15 days. And the first monitor was recorded in 1987. In the second time period, the 3 active injection wells, H3, H4, and H5, were converted to producers. And then they picked a new injector well, H6, and steam was injected for a period of 96 days. So the second monitor was then recorded in 1988. And finally, in the third time period, steam was injected into 2 producing wells for a very short time period, and then it was injected into the main injector well, H6, for a period of 6 months. And then the third monitor was recorded in 1989. So that gives you a kind of background of the actual steam injection process that was used in this survey. So obviously, when we're doing time-lapse, we want to actually highlight changes in production. So when we did an amplitude difference between the base survey and the first monitor survey without any processing at all, and this shows the sonic logs inserted, you'll see that really there's not a lot of indication of where the production is. So the blue horizon here is the base of oil sand, and the top of the base of reservoir are indicated on the log. And the red horizon is the top of the complete interval. So as I pointed out, the anomalies do not stand out in that zone. So let's have a look at the time-lapse workflow that we use in Pro4D. First of all, we find the overall correlation coefficients and shifts, and we apply them to the monitor, each monitor in turn. We then compute and apply an average phase and time shift. We then compute and apply a shaping filter. We then normalize the amplitudes. Then we compute and apply the shallow statics. And then step 6 is to compute and apply time variant shifts. And then, of course, after that, we interpret both the delays and the amplitude differences. And of course, the delays and the amplitude differences are telling you the same information, but they can be interpreted differently. With time delays, of course, indicate velocity differences. Amplitude differences also indicate velocities, but they can indicate impedance differences and so on. Today, I'm going to focus on step 6 and how to enhance it. So here's the amplitude difference between the base survey and first monitor survey before time variant shifting. And you can see that there's a lot less amplitude distortion. There's much better indication of where the reservoir zone is. So there's some interesting production anomalies. However, there are still many extraneous artifacts below the base of the reservoir. And that's what we're going to try and reduce with time variant shifting. Okay, so the basic method we've used since the start of the program is simple cross-correlation. So recall that the theory for cross-correlating two vintages of seismic data, which I'll call V1 of T and V2 of T, can be written like this. The cross-correlation coefficient as a function of T and tau, where you shift, basically you shift the second monitor with respect to the first monitor, or vice versa, the first with respect to the second, from some maximum lag, negative maximum lag, to a positive maximum lag. So tau is the lag, and each time you apply a shift, you simply sum the amplitudes, the product of the amplitudes of those two traces. I think you should be fairly familiar with the cross-correlation method. In the case of time variant shifts, we use short correlation windows, which we define throughout the reservoir zone, and the shifts for each window are computed. Then we interpolate the shifts between the windows, and then these time variant shifts give the time delay information required for interpretation. And also we can remove them so that the difference amplitudes can be correctly interpreted. So the shifts have a twofold purpose. You can interpret the velocities, and you can also interpret the velocities from the shifts, velocity changes in the reservoir, and you can also apply them so that the amplitudes are correctly differenced. So here's the time variant cross-correlation coefficients and time shifts between the base and monitor 1. And you can see the shifts are quite large and quite noisy. So and that's the correlation coefficients on the left-hand side of this plot show that the good quality, the good qualities are shown by the purples, and the medium qualities by the yellows, and the really bad quality are shown by the browns. Okay, so the shifts shown on the right are fairly large and could be improved. Now let's look at some of the other monitors. Here are the correlation time shifts over a constant time slice of 214 milliseconds, which was centered on the production. Note again, they're quite noisy, but as we would expect, they actually are showing some interesting information as we go from monitor 1 to monitor 2 to monitor 3. And I'll indicate the wells here, we're actually seeing the negative time shifts associated with that H6 well. Which, of course, negative time shifts indicate that the velocity is going down due to the steam front advancing within the reservoir. Now, one way to improve the time shift quality is to keep only those time shifts within a range of high correlation and expected time shift. So here's a cross plot which shows cross-correlation times on the horizontal axis and cross-correlation coefficients on the vertical axis. So what we do is we pick a zone that includes only the negative time shifts, those are the ones we want to keep, and also the correlation coefficients greater than about 55%. So when we apply that, notice there's the time shifts before conditioning on the left and after conditioning on the right, and they're much smoother and of course less indication of those spurious positive time shifts. So what we do now is I'm going to show the correlation coefficients on the 3 time shifts, and now you can see there's a much better indication of that steam front advancing on the right-hand side, or the eastern side of the reservoir, especially in the area of the H6 well when we get to the third scenario, or the third monitor. Now, once we apply those shifts, notice now that we've done a much better job of removing the extraneous artifacts below the base of the reservoir, and also we've improved the look of the anomaly between the top and base of the reservoir. Okay, so those, of course, are revealing the production-induced shifts. Now, I mentioned also we could do amplitude changes. Here's the normalized root mean square amplitude differencing between the base and each monitor survey after conditioned time variant shifting. NRMS is simply the normalized root mean square average. It's a common way of normalizing differences between surveys, and we did the averaging between horizons 1 and 2. Obviously, you'd get different results depending on where you did the averaging, but we felt that was a reasonable zone to look at the averaging. And you can see just a small amount of change between base and monitor 1, a larger amount of change as the steam front advances between base and monitor 2, and by the way, I'll put the wells on here, and a much larger change by the time we get to monitor 3. Although H6 doesn't show as much change as we'd expected, H5 may be a little overly shown. And there's also some areas up here just north of, the top part of the survey, north of H3, that maybe are a little, don't really fit the interpretation. So let's start by talking about this, the new Taylor expansion method. It's based on a paper by Naini et al. In 2009, where they propose a multi-vintage time shift estimation procedure that was based on earlier work by Hatchell from Shell, Hatchell et al., on 4D geomechanics reservoir modeling. So they start by assuming that 2 vintages of seismic time-lapse data only differ by a shift of tau 1, 2, the change between 1 and 2, and they can be written as a Taylor series expansion like this. So notice we're, instead of the functional relation V2 of t as V1 of t plus tau 2, we now linearize it using the first term in the Taylor series expansion, where the V1 prime term is the derivative of the V1 vintage of data with respect to time. So if we take the difference between the left and right hand sides of this equation, we can minimize it by setting the derivative with respect to the time shift equal to 0. So we differentiate f of 1, 2 of tau 1, 2 with respect to tau 1, 2. And that simply involves, if you look at it, differentiating this squared relation, the sum of the squares of the difference. Now, I won't go into the full mathematical derivation here, but 2 things I should mention is, one, that the expression can be extended to multiple vintages, and also to the symmetric time shift, T1, which should be the negative T of T12. So that will stabilize the solution a bit. So without going through the detailed calculation, this gives us the following relationships, that T12 is equal to B21. Well, you can read those. I won't read them out to you, but they're basically a function of the sum of the squares of the derivative volumes. So A is related to V1, A12, A21 to V2, the derivative of V2, and the B terms are the differences between V1 and V2 multiplied by V1t. So notice the cross-correlation procedure is now replaced with a differentiation procedure. So it's much more robust. So now we note that we can compute the shifts simply from the traces in their first derivatives. So again, as in cross-correlation, the shifts are computed with a sliding window. So let's apply this now, and here's the comparison between the cross correlation and Taylor time shifts. Notice now we have not done any preconditioning, so that, and by the way, that little green dot just when I captured the screen, that was where my cursor was, so it doesn't indicate really any anomaly. Should probably recapture it at some point. Anyway, so you'll see the shifts aren't as large, but they're predominantly negative. They aren't as large as the cross correlation time shifts. Okay, much less noisy as well. So here's the application, and you can see that note the time shifts are now dominantly negative without the use of a filter, of a preconditioning filter, when compared to the cross correlation approach. And what's very nice about this is it shows in the H6 region there's this strong anomaly, as you might expect. So there's the wells indicated on here. And here's the difference, and the amplitude difference. Again, we've removed many of the extraneous artifacts, and we're showing some interesting anomalies, slightly different than the previous method, but they're still showing in the top to base reservoir interval. So these are of course the production-induced shifts. And here's the amplitude change. Now, what's interesting now, compared with the previous result, well, again, you see from monitor 1 to monitor 2, monitor 3, the steam flood's expanding, but now we are seeing indications around the H6 well, which we expect, and we're seeing less of an effect which in that zone north of the H3 well, which seems to make a little more sense physically. All right, so let's now go to the second option, dynamic time warping. It was first developed for voice recognition by Sacco and Chiba in 1978, a paper called Dynamic Programming Algorithm Optimization for Spoken Word Recognition. It was used to stretch and squeeze speech to match the stored voice pattern of phone conversations. And Dave Hale, a brilliant researcher who's recently retired from the Colorado School of Mines, adopted the algorithm for seismic processing and published a paper in Geophysics in 2013 entitled Dynamic Warping of Seismic Images. The algorithm is very useful for lining up seismic images from various things, pre-stacked data for AVO effects, multi-component data, and what we're going to use it today for is different time-lapse vintages to determine the time variant time shifts. His algorithm has been successfully incorporated into Pro4D, and I'll briefly review the theory and then apply the method to the GLISP data. So mathematically, for a single vintage, dynamic time warping finds all the shifts simultaneously now by minimizing the sum of error for all possible lags. So here we're saying, let's look at all the possible lags, L of t, where L of t is an interlag, and let's minimize the error between the time and all possible lags. Another important aspect of dynamic time warping is that it's constrained so that the lag between successive samples cannot exceed plus or minus 1. In other words, tau of t minus 1 is less than or equal to 1, which is important so you don't have busts in the actual result. So here's cross-correlation versus dynamic time warping shifts. And you can see, although there's some negatives now, some positives, it's still predominantly negative. And there I'm comparing it with the original cross-correlation time shifts on the left. So again, they're much less noisy. And here's the dynamic time warping shifts over a constant time slice of 214 milliseconds. Notice they're less smooth than the Taylor shifts, but still predominantly negative. And when we get to base minus monitor 3, again, we're seeing that negative anomaly around H6, which was the major injector, which we would expect. Here's the amplitude difference between the base and the first monitor survey after the dynamic time warping shifts. Again, we've reduced many of the extraneous artifacts, but we've revealed the production-induced shifts, although they're a little different than they looked on the previous two examples. Here's the normalized root mean square amplitude difference, and you can see now that looks similar. Again, not much happening after the first injection period. After the second injection period, you're starting to see a lot of amplitude differences at H4, around H3, and then in the last survey, we're seeing a lot of activity around the or coming close to the H6 well. So until now, all of our dynamic time shift calculations have been in the vertical direction, vertical time direction, or you could say depth. However, we do know that the injection of heat or fluids into the reservoir will also affect the horizontal stresses and create inline and cross-line shifts. So in 2009, which was prior to the work on dynamic time warping, Dave Hale had published yet another paper in geophysics entitled A Method for Estimating Apparent Displacement Vectors from Time-Lapse Seismic Images, which proposed a way to compute all three of the shifts. Now, since his method's an extension of the correlation equation showed earlier, I'm going to show very quickly how we can extend that to the vector case. So here's the problem. Now we want vector shifts now. We'll call them J1, J2, and J3 using the terminology that Dave Hale used in his paper, where J1 is vertical time or depth shifts, J2 is the inline shifts, and J3 are the crossline shifts or directions. And, sorry, these are the directions, and then U of J1, U1 of J, U2, there's a little slight typo there. I should have corrected it. That should say U1 of J, U2 of J, and U3 of J is a vector of displacements. So in the displacement vector computation, Hale used cross-correlation, but he now extends it to 3 dimensions and applies a weighting function. So he applies it by an exponential weighting function, exponent of k dot k over 2 sigma squared, where sigma is simply a radius around. It's almost like a you're looking at the variance or the standard deviation around the well. Sorry, around the area you're applying it to. So the use of Gaussian weighting is why we call the option 3D warping by Gaussian correlation, but we could equally have called it 3D displacement vectors. In fact, that might have been a bit more descriptive. So here's cross-correlation versus Gaussian correlation, or the displacement vector time shifts. So this is in the vertical direction, and now again you see they're less noisy than regular cross-correlation. Here are the shifts over a constant time slice of 214 milliseconds, and notice a very interesting thing now, they're much more continuous and spatially oriented than the previous ones, and you can see when we get to basin monitor 3 how that area around H6 has expanded. And if you'll permit me a very bad joke, if you look at the middle, the base minus monitor 2, this is really an interesting footprint. I better stop there. Anyway, so we look at the that was the time shifts. We can also get 2 other volumes of shifts from the displacement vector calculation: the inline shifts and the crossline shifts. So here's the inline vector shifts on the shown on the left, and the crossline vector shifts shown on the right, where these are in terms of incremental traces. So it goes from plus 1.5 trace in the dark red to minus 1.5 traces in the blue. If we look at the time slice at 214 milliseconds, it looks very interesting. And now we're seeing these are the time shifts. They seem to be very similar to what we saw in the previous studies, except we might be seeing a little more effect in monitor 2, the difference between base and monitor 2. But we're seeing strong effects in base minus monitor 3 as well. Although H6 is now a little slightly positive. Now here are the crossline shifts, and as we might expect, they indicate that there's kind of a gradual transition from positive to negative shifts at injector wells H6, H4, and H5. Again, we don't know what really to expect when we eject in terms of the crossline shifts, but actually those were the let me just compare with the inline shifts again, so you can see a kind of halo effect around the reservoir, as you might expect. Likewise, now we're in the cross-line shifts, we're seeing a kind of a vertical effect. Probably one of the things we should be doing is taking the square root of the sum of the squares of these two to see the overall kind of vector shifts. That's something we'd probably put in a future release. And here's base minus monitor 1 difference after displacement vector shifts, the full displacement shifting. So now you're applying all 3 shifts, and again you're seeing the extraneous artifacts being removed below the base of reservoir and the production induced shifts being shown. When we look at the RMS, or the normalized RMS amplitude difference between horizons 1 and 2, it's very interesting. It's consistent with what we've seen before, but now we are seeing again a kind of more scientifically expected result, that the main changes in the amplitudes are around H6, H3, and H4. Some of that extraneous information that was shown on the original time shifts is not shown. So the recording history of the GLISP pilot. First of all, I'm just going to review it before we compare the results to see which ones we think are more consistent. Remember, the first time period we had very short steam injections in H3, H4, H5. Second time period we brought H6 on board. We converted H3, H4, and H5. So H6 was steamed for 96 days, and in the last time period, H6 was steamed for a period of 6 months. So that should be the major effect we see. So when we look at the Gaussian correlation time shifts over a constant time, you can see that essentially when we look at condition correlation all the way through Taylor expansion shifts, they're all giving a consistent picture, but I would say by the time we get to Gaussian correlation, we're seeing a much more detailed map of what's happening around the reservoir, around the injector, H6. But it is nice to see they're all fairly consistent. Okay. Then when we look at the normalized root mean square amplitude difference, again you can see what's very nice about this is Taylor expansion, the dynamic time warping, and the Gaussian correlation are all quite consistent, and condition correlation shows some extraneous anomalies. So I would probably pick one of the other ones as my product. In fact, I would probably say because the Gaussian correlation has all 3 components computed and applied, it's probably the most scientifically robust or most advanced method. So again, here are the wells. And so just in conclusion, I compared 4 options in Pro4D for the computation of the time variant time shifting between base and base survey, and 3 monitor surveys in this GLISP project. We looked at condition cross correlation, the Taylor series expansion method, dynamic time warping, and dynamic vector warping with Gaussian correlation. Of the 4 methods, the Taylor expansion shifts, dynamic time warping, and Gaussian correlation vector warping appear to give the most consistent and reasonable results, more so than the original condition correlation method, although the cross correlation method also gave reasonably good results. And also the big advantage of the Gaussian correlation vector warping is it produces inline and cross-line shift information in addition to time shift information. So I'd like to thank the following colleagues at Hampson Russell: Francis Ma for being the initial chief developer for Pro4D and for implementing the Taylor expansion method, Tim Yu for implementing the dynamic time warping algorithm, and Tiancheng Song for implementing Gaussian weighted vector correlation. Thank you very much, and I'd appreciate any feedback.